So sometimes in order to be able to find the antiderivative, we're going to have to be able to reverse the order of integration to make the antiderivative easier to find. And in this case, and honestly in most cases, it's best to draw the region R by hand, so that way you have a sense of where to go. Okay, so we're going to look at, we're in the XY plane, right here, X and Y. And then when we look at this, it says Y equals the square root of X, which we all know what that graph looks like. It looks like this. Right? We've seen that graph for a long time in our lives. And then Y equals 2, right? Y equals 2 is up here. And of course, we need to know their point of intersection. So let's find that real quick. We could do this with Desmos as well, or with Maple, but this one's particularly easy to do. So we want the square root of X equals 2, so X equals 4. All right, so our region of integration is right here. And the way it's currently written with that integral is that we're doing dy dx. However, dy dx would not be useful for us because, I mean, we could do it, but the integration would be really hard to do because of the y to the 5th plus 1. Whereas if we did x first, there's only one x in there, and that'd be really easy. Okay, so we want to switch this to dx dy. Now, dx dy is a horizontal box, right? So going that way is dx dy. Okay, so I'm going to have to change my limits of integration here. So this is the tricky bit. So the integrand doesn't change. It's x over y to the 5th plus 1. And we know we're going to go dx dy. So let me put dx right here. And then dy will go after it. There, I popped in the dy. Okay, so x, or actually y. Y is really easy because you just have to go from 0 up to 2, right? So your y values. So 0 and 2, remember that last integral has to be constants. So that's great. But now we need to figure out the left and the right-hand edge of this box to figure out our x values. Well, the left-hand edge is easy. The left-hand edge is x equals 0, right? So I'm going to have to make a little comment here. The left would be x equals 0. Over on the right, that was y equals the square root of x, but that's no good to us because that is solved for y, and we need it solved for x because we're doing dx as our differential. So we would say, all right, if y equals the square root of x, then y squared equals x, and that's what we're going to put in, like that. All right, and then from here, we're going to just integrate it. Now remember, y to the 5th plus 1 is a giant constant. It doesn't mean anything to this dx differential. So all we're going to do is 0 to 2, and then the integral of x is 1/2 x squared. So we're going to integrate that. I'm going to put the 1/2 out in front. And then it's x squared over y to the 5th plus 1 dy. Right? So 1/2 x squared is the integral of x with respect to x, and the y to the 5th plus 1 is just sitting there, right? And now we're going to take this from x equals 0 to x equals y squared. And again, you don't have to write the x equals in there, but sometimes I like to because I just want to remind myself of what the heck I'm doing, right? Okay, so I'm going to put y squared in here, and then the x equals 0 doesn't really do anything for us because this is a polynomial on the top. So this is the integral, 1/2 integral from 0 to 2. And it's y to the 4th, because y squared squared would be y to the 4th, over y to the 5th plus 1 dy. And this particular integral is so easy. I think we'll actually keep going and do it all by hand just to prove to ourselves we know how to do this, because it's a u sub, and it doesn't hurt to remind ourselves how u sub works. So u would be y to the 5th plus 1. Then the derivative with respect to y would be 5y to the 4th dy, which is what I have, y to the 4th dy. I just don't have that 5, so I would do 1/5 du equals y to the 4th dy. Okay, so then I'm integrating 1/2 integral, it'd be 1 over u du, and then I'd have a 1/5 out here in front. All right, so that's 1/10. Now notice I didn't put numbers in because those numbers are y values, not u values. So I just left the integral as it was, right, as in that I'm going to have to integrate, but I'm not actually putting in any values. All right, so the integral of 1 over u is the natural log of the absolute value of u, right? And then I'm taking this from particular y values. So u equals something to u equals something. Now you could go find the u values, right? It'd be u equals, well, let's think here. If I put in 0 for y, if y was equal to 0, u would be equal to 1. If y was equal to 2, u would be equal to 2 to the 5th, which is 32, plus 1, which is 33. So if you want, you could put, let's see, 1 and 33 in here, and then put 1 and 33 in here, and never go back, if you don't want to the original, right? We can do that. Or we can go back to the original if you like. So this is 1/10 natural log of 33 minus the natural log of 1, and the natural log of 1 is 0. So this is 1/10 natural log of 33. All right, so that's u substitution with no back substitution. Now, if you don't want to do that step, you can go back here and do 1/10 natural log of, what was it, y to the 5th plus 1, and then you're taking that from y equals 0 to y equals 2. It's going to get you the same answer. It's just going to take a little bit of work there. So either way you want to do it, you're going to get 1/10 natural log of 33. I'll just put an or in here, right? This is called back substitution, when you put back in what u was, right? So this will be 1/10 natural log of 33 minus the natural log of 1. It'll get you the same steps, and then you'll get the same answer. All right, let's go look at it in Maple, because we can always check our answers in Maple. So here's the object. So this is x over y to the 5th plus 1. And I again graphed 0 as well, so we could see the region of integration right there. There it is. I had to find my Maple code a little bit. All right, so there we have, see, you can see the region of integration right there if I look down, and then it's this object right here. And so we found the volume of that space between the xy plane and that multicolored rainbow surface. And if we want to check our answers, we can see that they are indeed correct. It is the natural log of 33 divided by 10. I double checked it by giving a numeric answer, etc. All right, so let's do another one where we have to change the order of integration in order to make the integrals work out nicely. Okay, so we have this integral right here that is given to us, and we want to change the order of integration. So first we have to figure out what the region of integration is, and that comes again out of our limits of integration. Okay, so we have x equals e to the y, and then we have x equals 1, right? So we know what x equals 1 looks like, right? X equals 1 is a vertical line right here, right? So that's x equals 1, no problem. Now, what does x equals the e to the y look like? Well, it's going to look like this. You could graph it on Desmos, you can graph it on Maple. It's going to look like that. It's going to come through 1, 0, just like the other thing does. Okay, so then we're going to stop, right, 1 and e to the y, but then we're going to stop at 0 and 1 for our y values. So y equals 1 for the y values up here. So this is y equals 1, this is x equals 1, and this is x equals e to the y. Let me graph them all in Desmos real quick so you can see them. Actually, I plotted them right here in Maple so you could see, right, that it looks like that. And I had to use implicit plot because, of course, plot implies y equals, and we have an x equals 1 here, so it would never graph that in just regular plot. So I had to do implicit plot. So there's what it looks like. Okay, now what's the region bounded by that? It's the region in here that's got those 3 curves, well, 2 of them are lines, as the boundary. Okay, so we need to find the intersection, of course, because that's going to help us. We know we're going to need it. Here, let's grab that. right? So this is x equals, So the intersection would be x equals e to the y, and y is 1. So that's e right there. All right, lovely. So now let's look at our limits of integration. So it was currently written as dx dy, but we want to switch it to dy dx. dy dx would be a vertical rather than a horizontal, right? So we're going to go dy dx like that. Okay, so let's write our limits of integration. We know that the integrand hasn't changed. It's going to be x squared plus y squared to the 1/2 power, but we're going to do dy dx. Now x is easy because we can see x goes from 1 to e. So 1 to e, no problem. We have constants there. Great. Now the y values, so we have to think about the bottom and the top. Well, the top is easy because the top is 1. But the bottom, right, so the top is y equals 1. But let's talk about that bottom curve for a second. So the bottom is the equation x equals e to the y. But x equals e to the y is not useful for us because it's not in y equals form. So we have to rewrite this with the logarithm because this is what logarithms are invented for. If I take the natural log of both sides, right, bring the y down, right, the natural log of x is y times the natural log of e, and the natural log of e is 1. So, or in other words, that's the definition of a logarithm. So y equals the natural log of x. So that's going to be our other limit of integration. Natural log of x right here. Okay, so you might be thinking, well, why are we doing y first? Well, because if this is u, if u is x squared plus y squared, then the derivative of that with respect to y would be 2y dy, which is what we want other than the 2, because we only have a regular y here. So we want 1/2 du equals y dy. Okay, so keep that in mind. So let's rewrite our limits of integration. So we're going to go from 1 to e. Then we're going to have an integral from something to something, right? Some u values of some kind. And we could find them, but it'd be ugly because there's an x in there. So we're not going to bother. All right, and then we're going to say it's u to the 1/2. And then it's du. But we don't want all of du. We only want a half of du. So we're going to throw a half on the front. And then dx. And I don't put limits in there because I never found them. Those are u values that I didn't get. Okay, well, the integral of u to the half is u to the 3/2. So we know this is 1/2 integral from 1 to e, and then u to the 3/2, and then I'm going to put times 2/3 out in front, right? And then dx. And though that u is taken from two values that I never found. So now I'm going to go back and find what that is. That's 1/3 integral 1 to e. And then I'm going to put back in what u was. U was x squared plus y squared. And I'm taking that from y equals the natural log of x to y equals 1 dx. Right, I still haven't done my dx part. All right, so now I'm going to put in 1 for y and natural log of x for y. So this is 1/3. Sorry, I wrote that too close. 1 second. All right, 1/3. And then this is going to get ugly, but of course we're not really that worried about it. The integral from 1 to e. So x squared plus 1 to the 3/2 minus x squared plus the natural log of x squared to the 3/2 dx. And of course, once it gets this ugly, we just make technology do it, right? This is what Maple is for. All right, so let me go grab Maple. So here's the plot, so you can see it, right? There it is. There's the region and so on. It looks like it's not the right region, but it is. It's the scaling is off on the x and y axis, so don't worry about that. And we get that the integral is 0.8916. So there we go. Put a squiggly equals 0.8916. And there we have it. Now keep in mind, if we knew, pretend, if we knew that x, y, z are in feet, for example, then this would be feet cubed because we had found a volume when we did this. Again, it didn't say that, so, but if it did, that's how we would do it.